So I would suggest we can wait 2 more minutes and then we can start.
Right.
Sounds great. Hi, Raj. Long time.
Hello, Teresa. Yeah, good to
How
see you
are
again.
you?
Well,
Yes,
good.
lovely to see you.
Doing well, more or less, yeah.
Mhm.
I don't have people in the waiting room anymore. I don't know. How about you, Linda?
Yeah, I would say we can start, and if people join later, I can let them in.
Okay, thank you. So, yeah, I would just like to welcome everybody again to one of the diffusion seminars that we've been having for a while now. And we're particularly glad that we can manage the seminar today, where we are really bridging all kinds of time zones. So the speaker today is for one speaker, Teresa Ubide, and we're really grateful to her because she's joining in at a very, very late hour at her place. She's in Australia, and that's why for all of you in Europe and North America, it's a little earlier than the usual time. So thank you for remembering and making time on your schedule to connect with us, even though it's not the regular slot that you have come to know. So yeah, I just do the usual of introducing the speaker and let Teresa speak. So usually we have two speakers and then we go through and talk about the two talks together. Today we have one speaker, so that makes things pretty straightforward. So we just go through Teresa does a talk and we have a discussion. But as you have seen in those of you who have connected before, in many of the other talks, that we start off discussing things from the talk itself, but we end up discussing a lot of different things about diffusion, zoning, plumbing systems, and so on. So we had a very big discussion in February, very enriching discussion. So we can continue on things like that. So with that, let me just quickly introduce the speaker today. So Teresa Ubide is connecting, as you see, from the University of Queensland in Australia, where she has been for 6.5 years now. She told me just before this, and I was surprised because it seemed like she moved to Australia just the other day. And before that, she did a postdoc at University College Dublin in Ireland. And before that, she had done her PhD in, I guess it was a joint program between Spain and Amsterdam at the University of Zaragoza and University of Amsterdam. And what she's been doing is been developing all kinds of tools to map various trace elements using the laser ablation ICP-MS, and I guess she'll be talking about some of that work today. But that's something that's been very useful to many of us in different things that we do. So without more words from me, I'll just ask Teresa to talk about the architecture of magma plumbing systems across space, time, and tectonic settings. Teresa, all yours.
Thanks so much, Sumit. And thanks so much, Linda. Thank you so much for organizing, for inviting me. It's a big pleasure to be here. I'm honored to be part of this seminar series, which is wonderful. And I really appreciate everyone who joined from different parts of the world. So that's, yeah, very, very nice. Thank you so much.
So
Sumit, would you like to stop sharing?
Now?
Yeah. Okay. Okay, so you can see my screen?
Yes, very good.
Perfect. Okay, so thank you so much again, all for being here. I'm really excited to talk to you about, as Sumit was saying, developing new tools to allow us to resolve fine details in the petrology of our volcanic samples. We can get new information on the architecture of magma plumbing systems across space, time, and tectonic settings. And the first thing I'd like to do is to acknowledge the wonderful people I work with who make it all possible and really fun. And these are my students at UQ, collaborators around the world. Thank you all very much. And these are all only some of them. But yeah, I just really would like to highlight all the fabulous work. Some of this work I will be highlighting here. So we know that magma plumbing systems have really complex, they can be vertically extensive, and they are dominated by crystals, by mush. And in this new paradigm of magma plumbing systems, of mush systems, we know that eruptible pockets can be small and transient. And so in this new idea of plumbing systems, we really are interested in understanding what are the tipping mechanisms that make the system change from growing over protracted timescales to suddenly erupting or perhaps accumulating metals that are essential for a transition to a sustainable future and renewable energies. And one thing that I find particularly interesting as well is to understand how plumbing system architecture may change depending on magma composition and therefore the geodynamic setting we have in different magmatic systems. And so in this new paradigm of mush systems, what we get at the surface is a mixed bag coming from this complex vertical system. So this is a very typical trachybasalt from Mount Etna, one of the most active volcanoes on Earth, which has phenocrysts of olivine, clinopyroxene, and plagioclase. And each of these crystals may be recycled from different portions of this mush system as the magma moves, makes its way to the surface. And it's interesting to understand that each of these crystals may give us information of different parts of the plumbing systems and different times before the eruption started. So if we visualize the chemical variations within these crystals, and that's something we can do using laser ablation mass spectrometry imaging, as Shumit was talking about, we can see that the zoning patterns may be a bit different, even if they end up in the same rock. So in this particular example, olivine, clinopyroxene, and plagioclase, they all have a very clear rim. The rim of the olivine is rich in nickel, in pyroxene rich in chromium, and in plagioclase rich in strontium relative to barium, suggesting that we have an injection of mafic magma before the eruption started, but the inner portions of those crystals are all different. So olivine looks a bit flat compared to, say, pyroxene, and that could be because many chemical species in olivine diffuse relatively fast, as you know in this seminar series. So if we keep the olivine at high temperature, the zonations may be diffusively reset. Plagioclase composition, so chemical elements in plagioclase normally diffuse slower, but it's also true that plagioclase stability field is expanded when we lose water in the magma, and Etna magmas are quite water rich. So we need to get to relatively shallow portions of the plumbing system for plagioclase to start recording processes. And in contrast, pyroxene looks really complexly zoned, and that's because it's stable across a broad range of conditions of pressure, temperature, magma composition, and water contents. And because diffusion is quite slow, it is able to preserve all of those processes. So it's interesting how we can unravel the mush by putting all these pieces of information together in space and time. And so what we're going to try to do in this talk is try to follow these processes that we can reconstruct through the mush in space and in time and through the dynamic settings. So let's have a look at some examples where we look at the usefulness we can have from pyroxene. And in particular, the concentrations of chromium, which we're visualizing here in this pyroxene, are really useful because chromium is an element that is abundant in mafic magmas, and it can tell us about those mafic recharge events that may happen in the plumbing system prior to eruption. So if we look at an interesting study for pyroxene, we're going to fly all the way to Mount Etna. in Sicily, in Italy, which is an extremely active volcano, and volcano, as you can see in this radar interferometry time lapse from the 1990s. So basically, you can see how the volcano inflates and deflates by millimeters to centimeters several times over the time scale of a decade. And that's because we can see how magma is recharging the system and magma is coming out during eruption. It's basically like you can see the volcano breathing is super active. And this volcano has not always been this active. It had been hypothesized, this increased activity and even explosivity, to be linked to the arrival of new magma at depth. And this new magma, being more primitive, would have been able to enhance activity in the volcano in the last few decades. So to test this hypothesis, we thought we would check if we could see these kind of processes on the chromium zoning of clinopyroxene crystals. So we went to the volcano and we sampled lavas from 1974 to 2014, so 40 years of eruptive activity. And we looked at the pyroxenes and we mapped them with laser ablation mass spectrometry for chromium to see if we could find chromium enrichments close to the rim of those crystals. And the results are summarized in this plot. So in the y-axis, we have time from 1974 to 2014. And in the x-axis, we have the percentage of clinopyroxene crystals that show this chromium enrichment up to 1,000 parts per million, so quite significant, close to the rim of the crystals, indicating that new magma is coming into the system with more mafic composition. With red circles, we have the data coming from eccentric eruptions. So these are eruptions that are able to tap into deep magma quickly and bring magma to the surface, rapidly bypassing the central conduits. And what we can see in these red dots is that the vast majority of the pyroxene crystals show that mafic intrusion or invasion as chromium recharge rims on the pyroxene crystals. In contrast, if we look at the central conduits of the volcano, we can see that in the 1990s, not many pyroxenes show chromium enrichment, but through time, we start to see more and more crystals showing chromium enrichment at the rim. And this basically tells us that this new invader magma that is efficiently tapped through those eccentric pathways is progressively through time invading into the central conduits of the volcano as well and driving up the activity and the explosivity in the volcano in the last 40 years. So this is really exciting because we can pinpoint who to blame for this increased activity and explosivity. And because we can combine this with calculation of timescales and calculation of depths from barometry, we can build an updated view of the plumbing system under the volcano. But that's not all. Doing this exercise, getting all these chemical images, we actually discovered many more things than we had anticipated. And one of the things that was very interesting to see is that many of the Etna pyroxenes were not just zoned in concentric variations. Many of the crystals, particularly in eccentric eruptions, were also sector zoned. So this happens when different orientations of the crystal growing along and perpendicular to the z-axis grow with different chemical composition. So basically along the z-axis in the sector called the hourglass, or the 111 if we use Miller indices, we have less aluminium than in the prisms that grow perpendicular to the z-axis, for example, 100. And so what we saw is that the trace element distributions, some of them followed the aluminium pattern, but some didn't. So the first thing was that initially we didn't look at the sector zone crystals in great detail because these are known to form when pyroxenes grow a bit more quickly. And so they are affected by kinetics of crystallization and they are more difficult to interpret. So we initially avoided these crystals to build that image that we've seen before of invasion into the plumbing system. But then we got really interested. So we went back and tried to see if we could get new information out of these trace element maps. And what we found is that actually it depends on the charge of the cation and the site it occupies in the lattice of the pyroxene as to whether it's going to develop sector zoning or not. So you can see here that highly charged cations, like high field strength elements, zirconium or hafnium or tantalum, are very strongly sector zoned. And we think this is because they're so highly charged, they can help balance charge balance substitutions introduced by the incorporation of aluminium perpendicular to the z-axis, preferentially along the z-axis, because aluminium is entering in tetrahedral position, substituting for silica. Aluminium is a 3+ cation, silica, who was there before, is a 4+ cation. So we introduce a charge imbalance, and we want to add as many highly charged cations as possible to balance the structure. And in contrast, low charged cations like chromium or nickel do not show as much sector zoning, and they still preserve that concentric zoning that tells us about the mafic recharge or the mafic invasion into the system. So what we can conclude from this is that not only we should not avoid sector zone crystals, but we should embrace them, because first, we can still obtain information on magmatic histories and magma recharge from the low charge cations like chromium and nickel. And second, the fact that we have sector zoning in highly charged cations itself is interesting as a means of understanding the thermal history of that magma. Because to get sector zoning, we need a low degree of magma undercooling. Magma undercooling is a difference between the liquidus temperature and the system temperature. And we can increase it by cooling the system and reducing the system temperature, or increasing the liquidus, for example, via degassing. And so if we increase the degree of undercooling, we would be able to generate sector zone crystals, but then if we increase it more, we would generate then skeletal to dendritic crystals. And this means that we can actually reproduce this process experimentally and try to see what the trace elements do as we increase the degree of magma undercooling in the lab, so that we can then bring that knowledge to better understand thermal pathways of magmas on the way to the surface. So this is what one of my PhD students, Alice McDonald, has been working on. So she's been working on the trace element budget of pyroxenes crystallized at different degrees of undercooling. And what she observes is that as the degree of undercooling increases, whether it is by decreasing the temperature or by decreasing the water content, the partitioning of trace elements, and in this case, what we're seeing is the partitioning of rare earth elements, increases very clearly. Even at high degrees of undercooling, rare earth elements can become compatible in the pyroxene structure, with implications for the evolution of magmas generated by fractionation of pyroxene in plumbing systems. But the other thing that this implies is that we can use the relationship between undercooling and trace element partitioning to generate mathematical equations that then we can bring to the natural samples to calculate thermal pathways during magma ascent. And so what we can see in this particular example of the 1974 eruption of Mount Etna is that the chromium-rich rims formed at lower degrees of undercooling than the chromium-poor outermost rims formed during ascent. And those are formed under lower degrees of undercooling than the microlights that form the matrix, that are the very last thing that forms in the rock. So we can actually track the thermal pathways of these magmas as they move up through the crust to eruption. And we can quantify these processes more precisely, which is really exciting. So this is really cool, and now we're also working on the best way of applying thermobarometers to these sector zone crystals, and that's something Alice is working on further. But let's move up from that deep zone that we were exploring with pyroxene, because pyroxene stability field expands at high pressure, to shallower pressure. So when we get to those shallower pressures, we start to lose water, and that expands the stability field of plagioclase. And so we start to get plagioclases that are forming with very complex zoning patterns, and we can explore them in terms of elements. But what we can also do in plagioclase is explore the chemical variations in terms of strontium isotopes that we can measure in situ. so that we can assess the consanguinity of the different melts contributing to the growth of the plagioclases in these shallower marsh systems. So how do we do this? We do this by coupling the laser to a multi-collector mass spectrometer instead of a quadruple mass spectrometer. And to see an example of this, we're going to now travel to Indonesia, so not far from where I am, and particularly to Merapi volcano, which had a really reasonably large eruption in 2010. And this eruption was quite explosive, and the explosivity at Merapi has been linked to a number of factors, including potential assimilation of carbonates from the crust that the magma is transecting on the way to the surface. So this is interesting because if we are transecting carbonates and we are assimilating CO2, increasing the explosivity of the magma, we should be able to see this in the strontium isotope ratios of the plagioclases that form at shallow depths. And this is something that had been proposed based on analysis of large megacrysts of plagioclase, where one can micromill individual zones and then do TIMS analysis on those macro sampled portions. But you cannot do these kind of things on many phenocrysts with very small zone growth zones that you find them in the majority of arc andesites in arc settings. And this is what we have here in this sample from 2010. So what we did is, with the laser ablation multi-collector mass spectrometer, is to analyze the strontium isotope ratio of each individual zone of the plagioclase, and also the matrix or the melt that brought it all the way to the surface. And we also had done analysis previously for elements, including anorthite content. And so the results, as you can see on the bottom right corner, are that the anorthite varies massively from about 40 to 90% anorthite content in this single plagioclase crystal, but the strontium isotope compositions are flat, and they are the same as the matrix that melts that is transporting the crystal to the surface, which is the gray band in the background. So basically, we cannot see in this particular eruption evidence for carbonate assimilation, but rather it seems that what we have are different degrees of massivity of melt and probably different water contents, where anti-gassed, water-rich mafic magmas coming into the system form high anorthite plagioclase, but with the same strontium isotope ratios because they're coming from the same source, essentially. So we are able to see all of this also in situ with strontium isotope analysis via laser ablation. So now that we've seen information we can get from the pyroxenes and from the plagioclases, the other thing I'd like to focus on is the melt. Because in these complex plumbing systems, we are generating crystals with different histories, but we're also filtering the melts as they ascend towards eruption. And if we want to look at the melts, the liquids, we should be able to isolate those signatures from the signatures imposed by the crystals we are recycling. And that's something we realized in a recent study on the island of El Hierro, the westernmost of the Canary Islands, just south of La Palma. And in this island of El Hierro, we have stunning examples of feeder dikes and associated lava flows, like the ones we can see in this image, where rocks may have different textures. So in this example, we have a dike with lots of olivine and pyroxene crystals recycled from the mush, and the lava doesn't have those crystals. And what is very interesting is that these two samples coming from the same system have quite different compositions, with the dike, which has lots of crystals, having almost twice as much the magnesium content as the lava from the same system. This highlights the problem of potentially whole rock analysis, in that if we have cumulate whole rocks, we will get very high magnesium content just because of the effect of those recycled crystals. So what we actually did was to look at the El Hierro data for crystal-free samples, and these are samples without crystals, aetheric, and also melt inclusions, even if the melt inclusions are trapped in mafic phases like olivine and pyroxene coming from depth. And what we found is that looking at these crystal-free samples, what we have is a volumetric peak of compositions at about 5% magnesium. And that's not only the case for El Hierro, but also many of the Canary Islands and many ocean island basalts in the Atlantic, Pacific, and Indian Oceans around the world. So this is interesting, first because we were not expecting this in an OIB, ocean island basalt setting. We were expecting very high magnesium contents, but this is not really the case if you look at the crystal-free samples. And that means that we are filtering those primitive melts, initially generated in the mantle source, to low magnesium contents of 5% through these complex plumbing systems. And so what we did is we modeled via fractional crystallization of primary OIB melts in upper mantle marshes or reservoirs. And what we found is that to get to that sweet spot 5% magnesium, we had to fractionate about 50% of crystals, decreasing the density of the melt without significantly increasing the viscosity, increasing the water content, so that in a melt that also has CO2, as we often have in an OIB setting, we would reach volatile saturation of this 50% fractionated melt at around the base of the crust, 10-15 kilometers, for example, in the Canary Islands. And this means that at this particular set of conditions, we may get to those ideal physical properties that propel the magma to erupt. And that's maybe why we get so many 5% magnesium liquids at the surface, as opposed to more primitive or more evolved ones. The other implication of this is that if we detect magma at this Moho level, by, for example, seismicity, we may have magma reaching that sweet spot and coming to erupt. And that's what happened in the eruption of La Palma at the end of 2021. But what's also interesting is that to follow this model, we need a magma with CO2 as well as water. And so this is something that we're going to expect in an OIB setting, but perhaps not in an ARC setting where we're going to have less CO2, and much more water. And interestingly, a recent study by Rasmussen and collaborators in Science in last year, 2022, found that not only water contents allow ARC magmas to store shallower, but also depending on how much water content you have, you store at a different depth. So basically what happens is if you have more water content, you saturate in volatiles deeper. When you saturate in volatiles and start degassing, you form crystals, and as a result, you increase the viscosity of the magma. And because the viscosity of the magma increases, you get storage zone. So not only water controls, so it's very clear here that not only water, but also the amount of water can have a strong control on the depth of storage in ARC magmas. And, because you have, going back to the comparison with OIBs, because you have much more water and not as much CO2, you are able to store at much shallower depths in an ARC setting, and you are able to promote differentiation of the magma, more explosive eruptions, and even porphyry copper deposits, which can accumulate the majority of copper that we mine today, which is essential for renewable energies. So this is all really interesting, and we can try to investigate this further with this new high-resolution approach where individual pieces of the puzzle come from individual crystal zones, from different minerals, and the melts that carry them to the surface. But not even like, if we don't even need to look at many different geodynamic settings, even within the single geodynamic setting, for example, magmatism generated by hotspots, we may have significant variations. So we may have a hotspot generating an OIB in an oceanic setting, but we may also have hotspots in the continent. And we may have hotspots having more or less strength with time. And in this sense, I'm going to talk briefly about a study that one of my former PhD students, Tamini, is going to publish in the next couple of hours. It will come out, and it's lovely study he did for his PhD in Eastern Australia. So these blue and red and grey symbols represent volcanoes in Eastern Australia that are age progressive. So in the north, you have all the volcanoes that have longer lifetimes and have larger volumes, and it represented in blue. And in the south, the volcanoes are younger, smaller volumes, and shorter lived. And so the idea is that this suggests that the hotspot that is linked to the development of these volcanoes as the Australian continent moved towards the north over one or several stationary hotspots was perhaps losing strength. The magma supply is certainly waning. And what we found very interesting is that the petrology and geochemistry associated with these variations was also changing. So if we look at the volcanoes in terms of whole rock analysis, we see that the northern volcanoes in blue have bimodal compositions, whereas the southern volcanoes, where the volumes of volcanism wane, they have a much more diverse range of compositions. And if we look at the more basaltic rocks only, even those are different to each other. In the north, the maficity, the magnesium number, is higher than the basalts that we have in the south. And this is at the scale of whole rock, but let's have a look at the minerals that we find in these different volcanoes. We find that in the south, where we have less volume, we find more phenocrysts that become larger in size. And they also have different compositions. So if we look individually at olivine, clinopyroxene, or plagioclase, we see that from north in blue to south in red, we lose forsterite. In olivine, we lose anorthite content in plagioclase, and we lose magnesium content in pyroxene. So the magmas that are feeding these volcanoes are becoming more evolved, more differentiated. And proof of that is that in the south, not only we have the typical titano-augite pink in color, we also have green clinopyroxenes that have much lower magnesium content or much higher iron concentration, which also reflect lower temperatures of crystallization, as we can see in the bottom panel. The pressures of crystallization we obtain are very similar, but these green crystals come from colder pockets of magma in these southern, shorter-lived and less voluminous plumbing systems. And the textures of the minerals also vary from north to south. So what we suggest is that in the north, when we have a higher magma flux, longer-lived volcanoes with more volume, we get more direct transport of magma to the surface, simpler crystals, and more mafic magmas, whereas as we move south and the magma flux decreases, we get more complex architectures of these volcanoes that lead to more evolved magma compositions with more complex crystals, texturally and also in composition. So that's really interesting, and it's taken from the opportunity to look at these Eastern Australian volcanoes in great detail, because we have 35 million years of activity covered in one single hotspot and all preserved across Eastern Australia. And from here, we have access to the Pacific Ring of Fire, where we are also excited to explore more on architecture of magma systems in arc settings. But perhaps to finish, the one last thing I'd like to say is that we've been exploring plumbing systems in space, with a change in depth, and also with tectonic setting and at different time scales. But, one thing that it will be really good to apply this approach to is to timescales that are very short as the scale of single eruptions. And this is something that was shown really nicely in this 2019 paper in Science that studied the Kilauea eruption of 2018. And it showed how the variations in whole rock geochemistry in the lavas were beautiful through the eruption and indicated the arrival of mafic magma into the system and heralded the arrival of more fluid magmas with time, which actually happened, and that was very useful. And so it will be very interesting. This is in whole rock, but it will be very interesting to bring this high resolution perspective of looking at the crystals and the melts separately, if possible, on this very short timescale, so we can feed into the petrological monitoring process. And so this is something that we tried to develop initially at Mount Etna with my former student Ruan Magui in the eruption of 2002, which is a beautiful eruption that is hybrid. It erupted magmas of different compositions from different vents in blue and red in these diagrams, where we have major, trace, and elements and isotopes in the x-axis and time in the y-axis. And so what Ruan did is to be able to track variations in liquid. He spent time carefully hand-picking ground mass matrix compositions so that he could see the signature of those liquids without the crystals that they were recycling. And he found beautiful variations in chemistry on the scale of days to weeks that we could then relate to monitoring signs. And this is something that we could not see in the whole rock data, which is represented in these diagrams with the hollow symbols. We could only see it because we were able to see those subtle matrix variations, but these took a lot of time. Hand-picking matrix is a very long process, and so it's not something we can apply easily or rapidly to, say, petrological monitoring or of eruptions. And so what our team is trying to do now is to try to do exactly the same thing, but faster, doing laser analysis on magmatic liquids, so matrices in our lavas and tephras, so we can analyze their elemental composition with the quadruple mass spectrometer and their strontium isotope composition with the multi-collector mass spectrometer. And so this story is to be continued, but yeah, we are super excited to continue deconstructing the mush by separating the pieces of the puzzle and bringing it all together. So thank you very much, and I'm looking forward to your questions.
Thank you, Teresa. That was a wonderful tour, actually, of all the different things one can do with the various trace elements and the various minerals, and also ground mass work that I just saw. So I'll let you get a drink and catch your breath a little bit. And
thank you.
All of you are very welcome to ask questions either by raising your hand, or you can type things into the chat and get going whichever way you think is suitable. I'm sure there's a lot of different geographic regions, a lot of different ages, and so I'm sure there are many different questions. Juan, you have a question. Go ahead.
Hey, thank you, Sumit. Thank you, Teresa. Can you hear me okay?
Yes, thank you.
Yeah, wonderful talk. Very interesting. I'm very curious. I have two questions. One is about the mapping. So typically in one swath, how many elements are you able to squeeze in? That's the first question. And the second one is about your results on Canary Island. You kind of talked about this 5% kind of a sweet spot for eruption. And from what you said, it sounds like it's a explosive eruption of some sort. And is that typical for OIB magmas? Because, when I kind of think about Iceland and Hawaii, it's more kind of like effusive eruption. So I was just wondering if the things that you see is related to the explosivity of the magmatic events.
Thank you so much. Great questions. Really appreciate it. So the first question was about how many crystals, how many elements we can map in one mapping experiment. And so what we normally do is analyze between 10 and 15. So we analyze less than what you would do in a spot analysis, because we don't want to compromise spatial resolution. If you analyze the entire periodic table, then you won't get a sharp image. So that's why we normally constrain to 10, 15. The second question, that's a great question. So I agree with you. OIB magmas more typically generate effusive eruptions, like in the Canary Islands, Hawaii. And so I'm not talking about those eruptions being necessarily explosive. All I'm saying is that we tend to have liquids of 5% magnesium in many ocean islands around the world. And we know that these melts initially were higher in magnesium contents when they generated as partial melts from mantle. So something has happened to filter them to 5. And so what has happened, we suggest, is that you get this fractionation process until you get to the ideal sweet spot conditions that make that magma come to the surface, coming from that base of the crust, but not necessarily explosively.
Okay, so
Right.
the crystals that you find are from effusive lavas, is that correct?
Yeah, so the rocks we analyzed were lavas and dikes,
Okay.
and we compared to data from OIBs globally.
Okay.
But the barometry on the crystals, which is another source of information, for example, in the Canary Islands or Cape Verde, also comes from that base of the crust depth. So it seems that this is a typical depth of storage in OIB systems.
Okay, wonderful. Thank you very much.
Thank you. Great questions.
Thank you, Teresa. So a quick follow-up on that MGO filter system. So do you have any sense of the time scale over which that happens, that filtration? Does it happen over days or weeks or months or years?
Great question. So, for example, in La Palma, after there was clear seismicity coming from that sweet spot depth, only a week after that, the eruption started. But there had been deeper seismicity building up over the previous years preceding the eruption. But it is true that when the strong seismic signals started to come from the base of the crust, only a week later, the magma was up at the surface.
So it's really fast. Fascinating.
Mm-hmm. But the buildup of that magma had been happening over years before the eruption started.
Yeah, so what'd be really cool is to see what happens earlier and what happens in that 1 week period. So in terms of chemistry, what goes on in the thing there. So
yeah, absolutely.
Something from the chat. So first, Wendy says, great talk. Thanks for the talk. So Lian Shuagi says, in the Canary Islands, is the final crystal filtering happening very close to the surface in the feeder dike? And how is that related to filtering process at deeper levels? So I think you're partly
thanks so much.
But can you elaborate on that?
Thanks so much. So what we find is that sweet spot 5 weight % MgO is reached after 50% of crystallization of primary OIB melts, with a set of physical conditions of viscosity, density, and water content that at depths at the base of the crust, when we get volatile saturation in a system with CO2, this is very important, we can get volatile saturation and potentially trigger the eruption at the surface. So that would be, so what we're saying is that trigger comes from the base of the crust, from moho level.
Okay. So does that answer your question, Lian? If not, you can speak up or try something.
Yes, please, if I haven't.
And while you're doing that, I'll take the next one. So Nick Barber actually echoes some thoughts that many of us are having. I'm sure that he says in a fantastic talk, but so many different thought-provoking things. So he's limiting himself to one question, which you don't have to. You can ask more than one. But I'll just read out the question that he has now. It relates to porphyry coppers. First of all, Teresa, you can also read the chat so you can get if you don't hear me well or something. But his question is, that the role the volatiles may play in porphyry copper formation, given the effects you noted for H2O for mush formation. Do you think particular mush processes like rheological lockup might promote or degrade the formation of porphyry copper? So basically, processes you are looking at, how do those relate to ore deposit formation?
Thank you so much, Nick. Lovely to see you in the chat. And thanks so much for the question. That's fascinating. I am very interested in answering this question. I think that's something that we can bring. Hi, I see you now. That's something we can bring from the volcanological perspective to the more economic geology world, to try to track these processes from a high resolution point of view. Work, as far as I know, work that has been based on PGEs, particularly find that, you know, you get this kind of sulfur saturation when the magnesium content is around 3, but this is all based on whole rock. So I am not sure how much of that PGE signature is coming from crystals, you know, particularly in an arc magma, it's full of crystals. So it's something I'm really interested in untangling. And yeah, so what do you think?
Can you hear me okay?
Yes,
we can
thank
hear
you.
Cool. Okay. Sometimes my headphones act up. Yeah, thanks for that. Yeah, I'm not really sure myself. I mean, I've been sort of thinking through these problems a lot, and I guess a lot of the thinking revolves around, you know, mantle source versus like structural controls. And it seems like the actual magma itself seems often left out of the conversation when we talk about these things. So I'm also thinking a lot about this. So it might be good to maybe take it offline and chat about it via email or something.
Yes, that'd be great.
Yeah, I mean, there could definitely be, I think there's definitely a lot of room for looking at active volcanic systems as analogs. I mean, lots of people have been making that point lately. So what you're doing definitely seems really useful for anything related to porphyry copper. So keep it up.
Yes, no, I'm super interested, but particularly in arc where you have so many crystals from everywhere, it's just a mess. So, you know, if you take a whole rock and you do all this high precision geochemistry on a whole rock, it's really interesting, but you don't know where the signature comes from. So I think there's a lot to say, and I agree active settings are cool because you can also combine your petrology with a gas monitoring as well, which is really good.
Yeah, and I guess the big question that I've always wondered, maybe you know more about this than I do, is, you know, with how porphyry copper deposits in particular form, it's a lot of question of stalling the magma at the right depth that you release those volatiles in kind of a big wave, you create the brecciation, a lot of depositing of ore minerals. But I think, well, I guess when that's modeled, how much of the rheology of the magma is taken into account. And if you're talking about mush tipping points, if you have enough interlocking crystals, maybe that contributes to, I guess if you have a mush versus a magma, maybe that contributes to earlier stalling or later stalling. So I guess I'm curious how the mush paradigm would affect our understanding of the rheology of these ore systems. I don't know if you have any thoughts on that, but.
Yes, I agree. And also not only the bit at the top where you get the porphyry, but also all the things that happen beforehand, because, you know, supposedly you have to have deep fractionation, you know, with amphibole and all these kind of things. And, you know, that's something we should be able to track with these high resolution approaches, but we haven't done yet because, you know, it's been more an economic question until now, but it's certainly super interesting. So yeah, I think there's a lot to do and I'm super interested. So yeah, we should chat.
Cool. All right, will do. Thank you. Thank you for your time and thank you for the wonderful.
So on that note, I'll tell all the others, because these are clearly topics that, you know, people can look at from many different perspectives. And I see many of you here who have different backgrounds. So if you feel like, you know, pitching into this or any of the other discussions, please, you know, just feel free to do that. And while people are doing that, so there are a number of comments coming in, Teresa, about how good and clear the talk was. And I think it'd be fair to say at this point already that, you know, we've had some great talks in the series, but this is clearly, and in terms of clarity, in terms of presentation, it's one of the very nicer ones. So
thank you. Thank you. That's a lot to say because it's a great series. Thank you.
They did really well. I mean, you know, it was really fascinating to follow, you know, how you, not just what you were saying, but how you were saying it. So I see a lot of students here as well, so that's good for them also to learn about, to kind of present their material. So let me see, there's a couple other things on the chat now. So Patrick says, in looking at an individual crystal or set of crystals, one can securely distinguish between a crystal exposed to a fresh injection of compositionally different magma and a crystal that just drifts into a compositionally different patch within its original host magma. Say, assuming given batch has some heterogeneity within it before magma. So one could perhaps get similar looking chemical and zoning signatures for very different processes. I can only use chat variant. I will talk again. Yeah. So basically, is it possible to get very similar looking zoning patterns, even though the histories of the crystals have been different? your thoughts on that.
Yes, thanks so much, Patrick. So there's a lot to say about that because first it depends on the minerals. So different minerals show up patterns of zonation and textural variations depending on different things. So plagioclase, for example, responds to everything and it's perhaps more difficult to untangle. Olivine may respond to things but diffuses faster, so it's harder to track unless you use slowly diffusing elements to look at the old record. And when you look at pyroxene, for example, that's also the case. It depends on the element you look. Things will be more or less diffused depending on storage time at high temperature. So for example, you look at chromium, which diffuses really slow and, kind of gets really nicely preserved. It's interesting to see that sometimes when you get a fresh injection of magma into the system, you may have crystals that have a very clear chromium enrichment. Others may have none if they haven't seen this recharge, in the whereabouts they have taken, because these are chaotic processes of mixing. And there's been some nice numerical modeling about this by Bergantz and collaborators. And sometimes they cycle through the magma and they may record more than one ring or rim of enrichment, depending on how many times they have seen this magma. And one of the things Alice, one of my PhD students, I talked about her sect zoning work before, is working on is trying to use zoning to track that kind of mush disaggregation. So if you get an eruption where you have new magma coming in and disaggregating the mush, trying to see if based on the zoning patterns and the zoning strength, if you can track back, the whereabouts of the crystals or the pathways of the crystals on the way up. So there's a lot to do in that topic as well. So it's really fascinating. Thank you for the question. I hope I answered.
Yeah, so there are more questions in the chat, but I'd like to follow up quickly on a couple of related things that I had on that. So first of all, so since you've been looking at all these different minerals, and I was particularly excited with the first one you showed about the Etna, where you had looked at pyroxenes, olivines, and plagioclase, and you explained a little bit about why there are differences in the zoning patterns of the different elements and different minerals. But have you tried correlating the zoning information you're getting from different minerals? So we started, doing that very early, and then because of the complexity of the plagioclase, we kind of, didn't quite dare to do that. But now you have a lot more information. So have you done some of that?
Yeah, that's great. I find that, as I said, I find that easy-ish to do for the rims, but as you move in, it becomes a mess because things get preserved differently and recorded different. So it's what you record and what you preserve, no? What we've tried to do is do that with the plagioclases from a 2021 eruption of Etna, and that's something also Alice is working on. And we found it really difficult, and we think it's genuinely because they are being recycled from different parts. So whereas the pyroxenes are recording more of the deeper processes, and they seem to show very similar zoning patterns regardless of what type of sample we're looking at, if it's from a fire fountaining or another type or more explosive volcanism. The plagioclases seem to be much more affected by shallow processes and degassing, and so it's actually something really interesting, but I find it really hard to do, because what I find is that, at least in Etna, in this detailed study we've taken for that eruption, they just show very different things. There are some previous authors that have tried to correlate, and I think the most reliable bits that can be correlated is at the margins, the very final bits, because the rest is just so hard. So I just think it's from different places.
Yeah, that's something to this whole community here. This is clearly quite a common situation in many different volcanic settings, that you can correlate the last event, the rims, quite well, but as you try to work your way backwards, it becomes more difficult. And maybe I can throw in a word of self-advertisement here. So one of the things we've been thinking and looking at is, so we deal a lot with zoning, and that's what this whole seminar series is about, zoning and diffusion. But what you also have is textural maturation. So crystals that are chemically stable actually dissolve and grow again. And that affects the zoning pattern too. And that's something I think we haven't been looking at as much, and maybe combining that with just growth and diffusion would help to address some of these complex correlations that we are not seeing there.
Yes, that's a very good point. The solution.
Right.
That's the other thing. Yeah, I agree 100%.
Next thing for all of us to try to get to.
Yeah.
But the questions here, I have something from Francois. So you showed these nice sector zoned planar pyroxenes at the beginning of your talk. Which sector do you think is in equilibrium with the melt, the high aluminum or the low aluminum?
Thanks so
Basically,
much, Francois. That's a great question. So it depends. So in the Etna crystals, we did a lot of work on trying to establish, and we continue doing it, what is better to use and what is closer to equilibrium. And because this sector zoning in Etna is related to very minor undercooling, both sectors are in equilibrium if you use a range of equilibrium tests. And I think the best estimate of pressure and temperature you obtain, if that's what you want, would be using the entire data set, so both sectors, as long as you have equilibrium with the melt. But that's in Etna. Other examples, so for example, Julia Hammer and her team worked on Hawaiian sector zone crystals, which are quite different because they have spongy textures, lots of disequilibrium, evidence for disequilibrium. And in that case, what they suggested is that the low aluminium seemed to be less, more reliable, let's say. No, that would be the assumption, because you incorporate aluminium under disequilibrium conditions. So then in principle, the low aluminium sector should be closer to equilibrium. But if your sector zone crystal has formed under low undercooling and low, conditions close to equilibrium, like at Etna, where textures are very euhedral and, there's no evidence of strong disequilibrium, you seem to get better estimates if you use all the sectors as long as they are in equilibrium. And that's something we are testing now based on experiments. And that's what we're finding. But I would love to hear your thoughts, Francois.
Yes, Francois?
No, I don't know. We can reproduce these things in experiments, indeed. I don't know if you have. Well, the sector zoning is coming from some kind of undercooling. But if a crystal is growing with changing undercooling, wouldn't you expect that, for example, the rim is going to is a rim you would not see this sector zoning? Did you see something like this, where mineral starts to grow with sector zoning and then it disappears? Or
good question. So often we see in Etna, for example, again, we see mantles that are sector zoned, and they are related to limited degrees of undercooling according to our calibrations. And then they are surrounded by final rims that are also sector zoned, but also seem to be more hopper in texture. And the rare earth element partitioning indicates higher degrees of undercooling according to the quantification we have done. So it seems that what we see in the natural record agrees with what makes sense, no? That as you move towards the surface, you increase the degree of undercooling, and because of that, you still have sector zoning, but you also have textures that are more hopper. They are not dendritic, but they seem to show more disequilibrium and they return higher undercooling. So yeah, it's really cool to be able to track that pathway and try to quantify it.
I mean, I'm sure there are other people here with opinions on this, but I'd just like to point out that if you're growing something with undercooling, then by definition you're not at equilibrium, and then the question becomes, what barometer can you actually even apply? And the other thing is there are different models of how you make sector zoning. So one is, if you have something enrichment near the interface and gets trapped, so that has a different pathway versus if you have just different interfacial energies, so different surfaces grow with different contents. And if the second one is true, then both of those would be in equilibrium because they're different in concentration because the different interfaces have different chemical potentials, if you will. So if that's going on, I mean, that would be, if one can calibrate that, that'd be really powerful. But the question becomes, in a lot of these things, to what extent you can use a barometer if these things are under cooling by definition is not in equilibrium.
So this is work in process, but according to the experiments we have, when you start losing that equilibrium and you start not having reliable PT estimates, it's not that you have sector zone crystals, you have moved into the skeleton and dendritic crystals. The sector zone ones that are forming at lower degrees of undercooling where you can still seem to be able to rely on the equilibrium and barometry test because they return the experimental conditions.
So without too much error. Good.
Okay. But
yeah,
Teresa, this is work in progress, but that's what we are finding so far, which is quite good because good news because and the other thing is that many of these barometers and thermometers are based, well, all of them are based on experiments, and pyroxene in experiments is often sector zoned. So
that's a whole different can of worms. I don't know if you understand this discussion here, whether that makes it a good barometer or not. Maybe that's something for another discussion sessions because the principle of the barometer relies on there being equilibrium. So if you don't have equilibrium, I mean, you can have empirical calibrations of concentration versus pressure, but that's not the same as a barometer defined on equilibrium. So yeah, I mean, that's clearly a area where there's a lot of discussion in conferences. You see a lot of debate on that, and this is something we'll be talking about for some time to come, I think. But this is also the other thing I want to point to people here that as you see, we start from a talk and then we go off on other related discussions that are affecting our field here, and that's important for this seminar series, that we don't just do a question answer and discuss these things. Sorry, Teresa, you're going to say something.
No. I agree with you. 100%. Yes.
You don't have rest. You have more questions, which is very good. So Vincius says, do you usually see opaque minerals associated with those green clinopyroxene? And do they increase with the arrival of the clinopyroxene variation? And if so, why do you think that happens? So do you have opaque minerals? What's their connection to pyroxene chemistry?
Yes, so that's a very good point. And it's very common to have magnetites with titanoaugite, for example, that's in alkaline pyroxenes. Well, that would be those with the pink pyroxenes. And interestingly, when you have arrival, so in an alkaline setting, when you have arrival of mafic magma into the system and your pyroxenes grow with higher chromium content, they often have these inclusions of magnetite associated with that high chromium zone, because you have this maficity, like spinel is often stable at liquidus, and so it would form, and that crystallization of magnetite will trap a lot of the chromium of the incoming magma, and that's why you often have very strong contrasts in chromium. So not only chromium goes up very much when you have mafic magma coming in, it also goes down quickly, particularly if you have magnetite crystallizing at the same time, because it traps all that chromium. So yes, that happens very often, and particularly in the pink ones as well, in the titanoaugites, you often have magnetite associated with them. Yeah, and they make the chromium zonations really sharp. They help.
So that again brings me back to those complex plagioclase things, because plagioclase is so sensitive to the water content. Do you think local variations in water content along a single plagioclase grain affect some of the zoning, and that's why it's so difficult so much more complex than the zoning in other minerals?
Yeah, it's crazy. So I guess, for example, those merapic plagioclases where you go from 40 to 90 anorthite for the same isotopic signature. So you must have changes in water content associated with, so it must be a melt that is anti-gassed and also more mafic, no? And those two things together are bringing the anorthite up so much. And that's something that has also been observed based on other bits of information like crystal zoning. Fidel has done work on Merapi, and also uranium series, Heather Handley also worked on that. So there's lots of pieces of evidence that suggest that there's, this arrival of mafic anti-gassed magma that what drives this 2010 particularly big eruption more than anything else. But yeah, so plagioclase is so difficult to interpret because so many things affect it at the same time. So it's very hard to, I guess, the good thing is that you can combine major and trace elements to try to see if it's magma of different composition what is contributing to the change. No, if the anorthite couples with minor and trace elements, it's more likely that it's a different melt composition. Than if you don't have that trace element variation coupled with the anorthite, and then it could be water contents
Okay, so now we have, so thank you again for a very interesting talk from Julius now. So from what I understand, analyzing the rims of the mineral phases would give clues to the latest magmatic event associated with the growth of the minerals. Is it possible to record multiple processes for each mineral? And is there a way to arrange which of these processes came first? So I think, you can give a very nice answer to that one. So what do the zoning tell you in terms of the multiple stage records?
Yes, thank you so much, Julius. So if you assume that the crystals are forming from core to rim, like the rings of trees, yes, you basically go back in time as you move from the rim inwards, or you go forward in time from the core to the rim. There's also a lot of evidence that says that if you have high saturation at the beginning of crystal growth and crystals start forming as dendrites, then this core to rim paradigm doesn't work, and that's been shown for olivine, for example. But if you have, let's say, a simple crystal that you see is growing in oscillations, and you can check this with a variety of elements, including slowly diffusing ones, then yes, I guess that's your question. You would be going back in time as you move into the core, if I understand correctly the question.
Yeah, I mean, that was the question, I think.
Yeah, and then the other thing is that you preserve those processes, because you may have an olivine that has recorded more processes that you can see at the end of the story, but because diffusion of many of the elements in olivine is so fast, you lose those upon storage at high temperature in the reservoir or in the mush system.
But if I may add, that if you have different plateaus, the compositional plateaus that are preserved, you can still do some of that. And there's some of that we did with the Carl et al. Papers in, Journal of Petrology, where we work back towards 2 or 3 different stages going back from the rim. So yeah, I mean, there are some situations where you can do that.
Yes.
And others where it's difficult.
Yes. Yeah, it tends to reset more, but you can sometimes get extra information. Thanks so much, Julius and Sumit.
Thank you very much.
Okay, great.
So, do we have other questions or comments, or things that you want to discuss, departing from what you've talked about?
John Michael.
Oh, I'm sorry, I missed that one there. So yeah, John Michael Auseio, I hope I'm saying that right. He's just curious about the age and volcanism progression in Eastern Australia earlier. Is it safe to say that they are derived from a single parental melt that wanes through time? And what could have been the reason why the phenocryst abundance decreases from one place to another? So 2 questions.
Thank you so much, John. Great questions. So Okay, so in terms of the source, there's been a lot of work on the Eastern Australian age-progressive or hotspot volcanoes, and they seem to have very common source components, and they seem to be fed by metasomatic sources, and perhaps that's why, even if we have a waning heat source, we still have magmatism, because metasomatic sources are easier to melt. So that's in terms of the first question. They seem to have a similar source. And then the other question was about the crystals. Yeah, so what we see is as the magma flux wanes, and we say it wanes based on volumes and ages. So the volume of the volcanoes decreases to the south, and the time span of the volcano also decreases to the south. We see more crystals that are bigger. So they seem to suggest that we are getting more complex or more mature mash systems as we decrease the magma flux. And so basically what we see is that as we decrease the magma flux, we are tending to promote storage over transport. Whereas at the beginning, where we had high magma flux, we had more transport than storage. And then we had less crystals, less crystal cargo, and smaller crystals, more simple plumbing system mechanisms. Whereas to the south, as we lose magma flux, we have more complex mash architectures, more complex crystals, and we often have reverse zoning. So we often find that we need mafic recharges to bring those magmas up to the surface. Otherwise, they just don't come up. So yeah, it's I agree with you. It's been a fascinating journey. I'm really happy for Tamini. He's done such a wonderful job, and his paper will be published in just over an hour in Nature Geoscience. So check it out. It's a nice story, I think. Thank you for the question.
We're getting a preview of a Nature Geoscience paper, so that's also always good to have. Yeah, I mean, it looked to me like that was a good answer, but if not, John, please, reflect. So yeah, looking forward to read the paper. He's happy. So now, so like I said, this is a good place to have some open general discussions. And thank you, Patrick, for kicking one off. So the open question is asking everyone actually, has anyone studied how to tell apart fine-scale uniform band zoning, perhaps due to slow mineral growth from a particular composition of melt, versus oscillatory zoning, which, if I understand it, has a chemical profile that is not uniform across each zone, but difficult to see. So the difference between fine-scale uniform band zoning and more oscillatory, I guess what you mean is without plateaus in between. Is that what you're referring to, Patrick? Yes. So
yes. So I don't know if I understand this. Patrick, thanks so much for the question. Great comment. So for example, in plagioclase, where there's lots of zonations, so the very small anorthite variations that you find on fine scale, those are, they are very small anorthite changes, and they are euhedral and very fine scale. Those are just related to the kinetics of the crystallization process. And then once you see more strong contrasts, and that they are not only in anorthite, but they perhaps are coupled to other minor and trace elements, then you can think of different magmas coming in. But what do you think, Shomit? Is this?
I don't know. This is really a question for everybody here. I mean, I guess it's also a question of a spatial scale, because used to be things that we called homogeneous before. Now we have better analytical tools, and we see there's a lot of variation within what we thought was homogeneous before. So yeah, it's just the word oscillatory zoning, if you put that in, since however long it has been known in plagioclase, there's just a lot of different ideas of how these may form, and they range from equilibrium partitioning of oscillatory conditions outside versus really kinetic disequilibrium effects that may cause it. So I don't know that there is a final word has been spoken on what oscillatory zonings are. So it'd be really good to hear actually what the views are around from different people around here, because I see many people here who have had quite a bit of experience in looking at different kinds of plagioclase crystals and other minerals as well. So yeah, he's saying just wondering about the strict use of oscillatory versus other types of fine scale banding, which might not be disequilibrium. Yes, very true. So when you, when do you call it oscillatory, and when do you call it, a number of different bands that are going up and down? Yeah.
So I guess one thing I can perhaps say, if this is something that you are thinking about for your own work, is so try to just describe what you have, like, and you say, I'm going to call this, I'm going to take, you have to decide on a naming convention. And if it's unclear where to put the threshold, you make the call, as long as you're clear about it. If that's what you are thinking about, you could just maybe say, oh, yeah.
Yeah, that's a very good tip for anything, actually, because, whenever there are a lot of things that we have in geology and geosciences where the definitions are not all that clear, but you can always define precisely what you mean by concept in your paper and then use that. That's very useful always. So yeah, Incius agrees with what you've been saying. Other thoughts, other comments on anything? Questions or comments?
I'm going to ask Diego. I see Diego in the audience. I know he was trying to do sector zoning. If this helped at all. I don't know if you hear me, Diego.
Yes, go ahead, Diego. You can log in.
Yeah, can you hear me?
Yes, hola Diego.
Okay, hola. Yeah, so you already remember I'm looking also about this sector zoning impacts from La Palma, and it's been as you commented, a very tricky thing. In the data we're working with, we tend to think about high aluminum sectors to be closer to equilibrium, because in rims we're seeing that the results are more or less similar to what we see in cores. So our thoughts go in this direction, but we are not completely sure. Yes, it is a quite difficult situation, and I don't have a definitive answer to this, so I'm not sure.
No, I was just curious. Yes.
Do you think that this could be possible, that high aluminum rims?
So that's two things that you're looking at, cores and rims. So in terms, so you would have to assess the conditions of cores and rims. In our experience, we've looked at the rims so far, and it seems that I think the key is that as long as you test for equilibrium using a range of tests for both sectors, you should be able to find which, like in my experience so far, both sectors are good as long as they are in equilibrium. That's the main thing, because, they may be, we found that some of the hourglass and some of the gneissons are not, and then you just get rid of those ones, but not necessarily choose one over the other, unless you have very strong case for that, I would say.
Yeah. Yeah, it's been really interesting. It's in fact the first time I'm looking at these things, and yeah, I found it quite a very tricky topic to look at.
Yeah, it's fascinating because that's why we're trying to constrain this better experimentally.
Yeah, it certainly looks to me like there are very old experiments people did back even in the 60s and 70s to understand that, and now it looks like it's time to go back and do a good series of experiments and try to understand that. Clearly a very good experimental project. Okay, other thoughts?
Thank you. I'm sorry I called you like out of the blue.
No. I mean, once again, this is really, the talk is really the launching pad for our discussion. So yeah, people ask the speaker, Teresa, and it's very good that the speaker also asked the audience. So
I just saw Diego and it's like,
it's supposed to be a two-way thing.
Thanks for engaging with us, Theo. And everyone, lots of questions. They're really good.
Yeah, so other questions or thoughts? I don't see any here, so I think, I'll try to bring this to a close gradually, Teresa, because it's also very, very late your time. And I think at this point, after a lot of discussion, and not just a great talk, but all of this discussion, I wouldn't be letting out any deep secret if I let you know that Teresa is giving this talk and going off on a maternity leave right away, right afterwards. So all the best for that. Have a great time. Thanks.
Thank you very much.
And that, makes it really even more impressive that you stayed up so late to do this. So really, very big thank you, Teresa. And,
big thank you for inviting me. It's been such a pleasure. Really lovely to see everyone, and thanks everyone for the engagement. So nice to see you, Simone.
And so we'll be back in April.
There's another question.
Oh yeah, let me see that here. Okay, so do we have a question? Yes, absolutely. We'll take that one. So if the magma is composed of melt crystals and gases, we can call mush a magma with more than 60% of crystals, or is it better to separate the two terms? Mush and magma. Or can you call it a mush and magma with? So yeah, the question is, how much of crystals do you need to have when you call it a magma or not a magma?
So it depends a bit on who you read, no? But it depends on the rheological lockup. And so, yeah, it's around 60% crystals when it becomes, when it becomes immobile, it's a mush. And then when you are able to remobilize the mush, is because you, for example, may have new magma coming in. So it's a good question, no? So what do we call each thing? I tend to use liquid or melt when I talk about just the part without the crystals, and mush when it has lots of crystals, no?
Yeah, but this is also a very good point for me to point to people that the older talks are also available online. And if you go back to the last talk in February, we had a long discussion on whether the issue came up whether people have a mush at all, or do you have crystallized plutons sitting down there? And there was all of you can go back and listen to that discussion on online to see what the thoughts were. But as you said, Teresa, that's kind of the current thinking on where mush versus melt is. But you have more questions now. So now Barbara is asking, can you see any, icons are coming up here. Can you see any signature change on trace element map of pyroxene zonation, which can be related to volatile change?
That's a very good question. So there is a bit of discussion around CO2 flushing affecting pyroxene textures, for example. Normally the one that is more affected by volatiles is the plagioclase, also because it tends to form when you are degassing. So it seems to be a broader recorder of this type of processes. But I've also seen literature where there's a discussion about flushing of volatiles imposing effects on pyroxene textures and potentially compositions. I'm not sure. Not a lot about this. I don't know, Shumit, if you.
No. But there are many people out here, so maybe if somebody does have an idea and a thought, please, chip in. So, but
great question, Barbara, by the way.
And you are the expert, one of the experts on that, Teresa. So if you don't know, we don't know. Figure it out.
Yeah, so I've seen suggestions of volatile flushing affecting compositional variations and texturals, but particularly in pyroxenes. Not so much. I think the question was about degassing specifically, and in that case, I think what you get, when you normally the pyroxene that forms shallower as you have ascent is like the microlites, the smaller microlights that form towards the surface, whereas the bigger ones tend to be from deeper levels.
Okay.
Can I
So
say something?
yeah, Mike,
Hello.
please.
Oh, sorry. Hi. Yeah, I was thinking that, I mean, CO2 flushing would decrease the water activity, so it would increase the undercooling, in fact. So you might see that in some of the trace element partitioning behavior?
Yeah, exactly. So
Potentially.
if you are able to increase the undercooling, then you would partition more, particularly the highly charged cations.
Yeah.
Because what you would do is, if you increase undercooling, you incorporate more aluminium, and because you need to charge balance, you incorporate all these other highly charged cations in.
So in essence, the crystal becomes a little less selective in what it wants to take up when it's undercooled. Undercooling is higher.
Yeah, it just takes all this.
The crystal growth rate should be faster as well.
Yes, and this is why many of these crystals, particularly when you have undercooling induced by degassing, shallower levels, these pyroxenes are typically just small. The microlights you form upon ascent, final ascent and eruption. Yeah, no, thanks. That's a great point.
You also increase the nucleation rates, so you form a lot more small crystals, but they're not growing very much. Exactly. Depending on how much the undercooling is, it increases.
Sounds like a great experimental project, Mike and Teresa.
Well, we're thinking about these things, but it's not so easy, actually. That's especially with nucleation involved, because it becomes difficult to handle all the things that influence it. Nucleation. But yes, there's no lack. But no lack of interesting things to do.
Yes, and I think it's also what Sumit said before, that the classic experiments that built many of these older ideas and calibrations, I mean, we have more resources now and different ways of doing things, so it's really, there's a lot to do. Yeah. Yeah.
So yeah.
Thanks so much for contributing, by the way. Thank you for chipping in.
Okay, so I'll look to see, there are, because if there are questions, we'll keep taking them. So that's the advantage of having one speaker, I guess, because kind of a very extended discussion. But I do think, we have a lot of thank you, Teresa, notes and for how good the talk was, the presentation was. And thank you all of you for, all the questions and the discussions and everything. That's what, makes this attractive and lively. So yeah, we will be back in April at the regular time. So that will be 4:30 Central European time, whatever it is, wherever you are in a part of the world. And that will be again a double header talk with, we'll send out the announcement. We have the speakers, we'll send out the announcement very soon. So I don't know, I see Linda here. Do you want to say something, Linda?
No, I can just agree that I will send around the announcements soon, as we already know the next speakers.
Right. So, and this will be, I'll tell you this much, this will be 2 great speakers that we have lined up for April. So be, plan your time and plan your calendars on that. Look forward to seeing all of you there. Thank you again. Thank you, Teresa, and have a great break and look forward to seeing you back. And
thank you very much, Sumit and Linda and everyone. Really enjoyed it.
Okay. Bye-bye.